Hello, in this video I'd like to talk about some old function notation that I found while researching the Krohn-Rhodes theorem. This is from Ginzburg's Algebraic Theory of Automata from 1968, although I've seen this notation from other sources from around that same time as well. It seems like this notation isn't used anymore, however, but if you know of any more modern sources that use this notation, please let me know. So instead of using our usual f of x notation, the text writes f of x as xf. And this solves the function composition problem. In traditional notation, f of g of x, the order of the functions is from inside out, which also means that it's from right to left, which I've seen confuse a number of undergraduates. In this case, xfg would mean to take x and then apply f and then apply g. We're applying our functions from left to right. And we can also, by associativity, interpret this as saying the function fg applied to x. And so fg represents g of f. In other words, it represents the operation of doing the function f first and then g second. One might wonder how we could deal with functions that take in multiple inputs with this notation, but we're actually already used to seeing these functions as functions that take in a single input, which is a pair, an element of the Cartesian product. And so we could write, for instance, a1, a2 phi to mean the result of applying phi to a1 and a2. Here I have an excerpt from the text that's describing the use of arbitrary functions to represent multiplication in a group or a semigroup. The notation handles relations the same way that it handles functions, and it's common to think of functions as a specific type of relation where x is related to exactly one y, and we call that y f of x. But in this case, it's actually useful to think of relations as a generalization of functions that take in an input and have a set of possible outputs for that input, a set of things that are related to a given x. And we denote this as xr. This agrees with the function notation as well as it can. It outputs a set, which is not quite the same thing, but we kind of have to. And as long as we can tell the difference between individual inputs and sets of inputs to the function or the relation, this isn't that big a deal. The notation then goes on to say, well, if we're allowing a set of possible outputs, why not also allow a set of possible inputs? And so if we have a set capital XR is going to denote the set of all things which are related to some x in our set, capital X. This might seem very abstract, but it's simply a generalization of taking the image of a set under a function. So for instance, if our relation is a function, let's say f, then capital XF is going to denote the image of our set x under the function f. And if we're really going to commit to viewing relations as a generalization of functions, then we should have a sense of composing two relations. Suppose that we have two relations, r and s, then their composition, which will denote rs in line with our function composition notation, it's going to be a relation that relates two values x and z if there's some intermediate value y such that x's are related to y and y is s related to z. If we're careful about elements versus sets of elements, this agrees exactly with function composition. But it's also a useful notation when we're thinking about relations. For instance, in set theory, it's useful to talk about double containment. Here I have an example of a set X which is contained within an intermediate set which is contained within a set Y. And we can denote this as containment composed with itself, or containment squared. And this is useful to write. For instance, one can do a Russell's paradox-like argument to show that no set can double contain itself, because if there was a set that double contained itself, we could carry out the Russell's paradox style argument and prove a contradiction. We can also use this exponent notation to describe transitive closures. If we have a particular relation R, we're interested in looking at the relation between x's and y's that are either directly related to each other, or x is related to some intermediate value which is related to y, or x is related to a sequence of two intermediate values which is related to y, or so on and so forth. And so if we combine our relation composition, our relation exponent notation, with as well thinking of these relations as sets of pairs of things that are related to each other, so we can take their union, kind of represent an OR type operation, then we have this very nice formula for the transitive closure of a particular relation. And this sort of series might look familiar. This notation is really ideal for dealing with automata. So suppose that we have an automaton with input characters A and B. Whenever we input a specific character, it's going to apply some function to the state that the automaton is in. And we can denote that function by that character. So A is going to be a function that takes in a state Q and outputs the state that will be in if we started off in state Q and read the character A. And the same thing for B. In this case, our function notation tells us that AB represents the function of reading an A and then reading a B. In other words, reading the string AB. So we can interpret any word as a function composition describing the behavior of reading that word into the automaton. And so we can very easily talk about, for instance, acceptance. We say that an automaton accepts a particular word if when we start off in the start state, which is denoted Q0, and read our particular word, that is apply W interpreted as a composition of A's and B's, then the resulting state that we wind up in is in our capital F set of accept states. And it's really useful, and with this notation really easy, to talk about the result of if we start off in one of a particular set of states and read a particular character, what's the set of possible states that we could wind up in after reading that character? And what's really nice is that this notation naturally generalizes to the non-deterministic case. In the non-deterministic case, reading a particular character can take us from one state to any of a number of states, possibly an empty list of states. And so again, we can think of these characters as these generalized functions that take in an input and have a set of possible outputs. Or equivalently, as relations, where, for instance, A relates P and Q if reading an A can take us from state P to state Q. In this case, relation composition, it works exactly the way that you would hope it would. The composition AB represents the relation, the generalized function, of first reading an A and then reading a B. It relates two states if we can get from one to the other by first reading an A and then reading a B. Just like how reading a character can put us into a list of possible states, we have a list of possible start states, which is usually denoted capital S. And the set of states that we could wind up in after reading a particular word, starting in the start state and following the transitions in some way, is exactly SW. And so we can say that an automaton accepts a particular word if SW contains a final state. And again, the notation SA represents the set of states that we can get to, starting from, S can be an arbitrary set here, starting from a set S and reading the character A. It's just that now we can get to potentially quite a few more states, depending on the non-determinism of the character A. So this is really great notation, not just for talking about automata, but for talking about functions and relations in general. And in fact, if you work with this notation enough, it almost feels like we're multiplying vectors and matrices, specifically row vectors whenever we're multiplying an element on the left. And it turns out you can actually follow this intuition to find a connection between automata and linear algebra, which I'll talk about in a separate video. But I want you to imagine the situation I found myself in as a graduate student. I needed to understand the proof of the Krohn-Rhodes theorem, and here was the proof in notation I wasn't familiar with. Here's a bit of the text that I had to decipher, and at the time I wasn't even sure if this was a relevant piece of text. There are a bunch of other topics that are also covered in the book, and I didn't care so much about those at the time. So consider the semi-automaton A equals SA sigma MA. This isn't standard modern notation for automata. First of all, these are semi-automata. They're not actual automata. A semi-automaton is just an automaton that doesn't have a final state. We're only interested in the operation of the automaton, not what state it winds up in at the end. But I had to, go back in the text and look up what notation were they using. They're using SA to represent the set of states. I'm more used to using a capital Q for the set of states. Capital sigma, we still use that for the alphabet. That's a very common choice. And then MA represents kind of the transition function information of the automaton, what each character does to the states. But it turns out that's not relevant because there's some other notation that makes it easier to deal with that, and we don't have to worry about MA. With the size of SA equal to n, so there are n states, and let pi be the decomposition of SA, the blocks of which are all subsets of SA having exactly n minus 1 elements. So for now, let's not worry about decompositions, but of course, in order to figure out that I didn't have to worry about decompositions, I needed to go back in the text and look up what a decomposition was. Let's just say that pi is the set of sets of states of size n minus 1, that is, sets of states that are missing exactly one state. For every S subset of SA and every sigma in sigma, the size of S sigma A is less than or equal to the size of S. Sigma A is just the function corresponding to reading the character sigma in the automaton A. So this is just saying that the image of that function on any set S will be smaller than S, right? If we have two inputs, two states, they could wind up getting mapped to the same thing, and that would make the image smaller. But everything's deterministic, so we can't make the image of a set larger than the original set. Hence, pi is an admissible decomposition. It can be used to construct a pi factor, A over pi, which we'll call B, of a very special nature. And again, don't worry so much about that, just know that we're constructing a new automaton B. Suppose the size of SA sigma A is strictly less than n. That is to say that the image of the character sigma as a function is not the full set of states. In other words, there's some state that does not get mapped to. There's some state that no matter which state we start off in, after reading the character sigma, we can't wind up in that state. Then there exists some hi in pi, that is to say that hi is some set of n minus 1 states, such that SA sigma A, the image of our state set, the entire set of states under the character sigma, is going to be a subset of hi. That is to say, the image of our set of states under this character falls into this set of size n minus 1. Again, there's some state that we cannot reach just after reading a sigma. And hi can be the set of states that omits one such particular state. Consequently, for every hj in pi, hj sigma A is going to be a subset of SA sigma A. Well, of course, so hj is a subset of our state set SA. Hj is in pi, so it's just going to be a set of n minus 1 states. And then we're going to take its image under the function sigma, And that's going to be a subset of the entire image of the function sigma. And of course, we already said that SA sigma A was a subset of HI. Then define H bar J sigma B. We're now defining the action of reading the character sigma on the states of our new automaton B. H bar, I realize it's capital. It looks a lot like HJ, which is a set of states, but H bar J is actually just going to be a single state of our automaton B. And we're going to define the state. So if we start off in state HJ bar and we read a sigma in automaton B, we're going to wind up in state H bar I, regardless of which HJ bar we started off in. That is, sigma B, the function of reading the character sigma on the states of our automaton B, is going to map all of the elements of the state set for B onto one element. It's going to be a constant function, which we can also say as the size of the projection of this function onto the second coordinate, if, again, we're thinking like a set theorist, that this function is a set of possible pairs, if the set of possible output values is of size 1. An input having this property of being constant, it will be called a reset input. And this is just one small portion of a several chapter proof, but I hope this gives you a clear sense of what it's like doing mathematics literature research and how having to adapt to this new notation made it that much harder to parse, even just to tell what various variables were. Were they sets? Were they elements? Were they functions? Just figuring out what was going on became that much harder because the notation was something I wasn't used to. Perhaps the most important takeaway here is that there's a lot of communicative value in sticking with familiar notation. I remember early on in my mathematical career being really excited about obscure mathematical notation, and particularly coming up with my own obscure mathematical notation. And that's a really good instinct. I remember creating my own notation to explore how e to the x turned addition into multiplication, and so you could use it to turn, for instance, integrals into product integrals. This is a very cool concept to explore, but looking back, the notation that I came up with would make anything I wrote with it very hard for other people and even my future self to read. So that's the flip side of the coin. Coming up with new notation is great for exploring new ideas and making connections between seemingly different areas of math. In another video, I'll explore the connection we found between automata and linear algebra in further depth. Also, just as natural languages like English change over time, mathematical language changes over time. What is familiar notation now might not be in another 50 years. So it's important to future-proof your work by explaining notation even if you think nowadays everyone would find it obvious. But even if you decide to fully stick to standard modern notation conventions, you still often find yourself with choices when writing mathematics. What variables do you use for various things? Do you use capital letters, Greek letters, decorations like hats and bars? Do you use them in a consistent way? When do you use subscripts and superscripts? If you have a simple idea like a function not being onto, how do you phrase it mathematically? Each one of these choices can make your proof a little bit easier or a little bit harder to read. There actually is something to be said about having harder to read notation in mathematics communication. Because I had to spend so much time reading this proof, trying to understand the notation and trying to understand the proof and the notation have stuck with me for nearly a decade now. Memory is, after all, the residue of thought. But I do try my best to use clear and easy-to-read notation in my mathematics communication, being careful to pick what variables I use to represent what things, and how I express various ideas mathematically, trying my best to explain what I'm doing in both words and mathematical notation. This is a very difficult task, and it requires a lot of practice to get good at. Clear communication in math is a hard but valuable skill, and it takes a lot of practice to become good at. A specific thing I'll note is the use of superscripts and subscripts. I really liked how the text used hi and hj to represent two different sets of n-1 states. This helped draw a connection between these two and avoided having to use a new letter. If we called one of these sets capital G and the other one capital H, it would be harder to see that connection between them, that they were essentially the same sort of thing. But I personally feel like having all of these superscript A's in the proof made it harder to read. Working with superscripts and subscripts is a careful balance between clarity and readability. It's particularly tempting to have subscripts within subscripts or superscripts within superscripts, especially if you spend too much time talking to computers, where whenever you have an input slot as a part of a definition, you can plug whatever you like into it, and the computer is perfectly happy to parse everything out. Look at this absolutely rubbish notation from my thesis. At least I then go on to spell out what I mean in words. So thanks for watching. The goal of this video is not to encourage you to go out and use this particular function composition notation in your own work. Please don't use this notation in your own work, but rather to draw your attention to the role notation plays in mathematics communication, and to encourage you to think about your own notational choices in your mathematics communication. Maybe try out various different choices and see which ones make the math more readable, and which choices make the math less readable. Anyway, be sure to leave any questions or comments you might have down below, and be kind to each other.